What I want to do in this video is talk about continuity. And continuity of a function is something that is pretty easy to recognize when you see it, but we'll also talk about how we can more rigorously define it. So when I talk about it being pretty easy to recognize, let me draw some functions here. So let's say that's the y-axis, that is the x-axis. And if I were to draw a function, let's say f of x looks like something like this. And I would say over the interval that I've drawn it, so it looks like from x is equal to 0 to maybe that point right over there, is this function continuous? Well, you'd say, no, it isn't. Look, over here we see the function just jumps all of a sudden from this point to this point right over here. This is not continuous. And you might even say we have a discontinuity at this value of x right over here. We would call this a discontinuity. And actually, this type of discontinuity is called a jump discontinuity. Continuity. So you'd say this is not continuous. It's obvious. These two things do not connect. They don't touch each other. Similarly, if you were to look at a function that looked like, let me draw another one, y and x, and let's say the function looks something like this. Maybe right over here, it looks like this, and that the function is defined to be this point right over there. Is the function continuous over the interval that I've depicted right over here? And you would immediately say, no, it isn't, because right over at this point, the function goes up to this point just like this. And this kind of discontinuity, this is the discontinuity, is called a removable discontinuity. Removable. One could make a reasonable argument that this also looks like a jump, but this is typically categorized as a removable discontinuity because if you just redefine the function, so it wasn't up here, but it was right over here, then the function is continuous. So you can kind of remove the discontinuity. And then finally, if I were to draw another function, so let me draw another one right over here, x, y, and ask you, is this one continuous over the interval that I've depicted? And you'd say, well, look, yeah, it looks all connected all the way. There aren't any jumps over here, no removable discontinuities over here. This one looks continuous. And you would be right. So that's the general sense of continuity, and you can kind of spot it when you see it. But let's think about a more rigorous definition of one. And since we already have a rigorous definition of limits, the epsilon delta definition gives us a rigorous definition for limits. It's a definition for limits, so we can prove when a limit exists and what the value of that limit is. Let's use that to create a rigorous definition of continuity. So let's think about a function over some type of an interval. So let's say that we have, so let me draw another function. Let me draw some type of a function. And then we'll see whether our more rigorous definition of continuity passes muster when we look at all of these things up here. So let me draw an interval right over here. So it's between that x value and that x value. This is the x-axis. This is the y-axis. And let me draw my function over that interval. Over that interval, it looks something like this. So we say that a function is continuous at an interior point. So an interior point is a point that's not at the edge of my boundary. So this is an interior point for my interval. This would be an endpoint, and this would also be an endpoint. We'd say it's continuous at an interior point. So continuous at interior point, interior to my interval, means that the limit as, let's say, at interior point C. So this is the point x is equal to C. We can say that it's continuous at the interior point C if the limit of our function, this is our function right over here, if the limit of our function as x approaches C is equal to the value of our function. Now, does this make sense? Well, what we're saying is at that point, well, this is f of c right over there. And the limit as we approach that is the same thing as the value of the function, which makes a lot of sense. Now, let's think about if these would have somehow been able to pass for continuous in that context. Well, over here, let's say that this is our point C. F of c is right over there. That is f of c. Now, is it the case that the limit of f of x as x approaches c is equal to f of c? Well, if we take the limit of f of x as x approaches c from the positive direction, it does look like it is f of c. It does look like it's equal to f of c. But if we take the limit, this does not equal the limit of f of x as x approaches c from the negative direction. As we go from the negative direction, we're not approaching f of c. So therefore, this does not hold up. In order for the limit to be equal to f of c, the limit from both directions needs to be equal to it, and this is not the case. So this would not pass muster by our formal definition, which is good because we see visually this one is not continuous. What about this one right over here? And let me reset it up. So let me make sure that that looks like a hole right over there. So we see here that what is the limit? The limit, and this is our c right over here. The limit of f of x as x approaches c, let's say that that is equal to L. And so that, we've seen many limits like this before, that's L right over there. And it's pretty clear, just looking at this, is that L does not equal f of c. This right over here is f of c. So once again, this would not pass our test. The limit of f of x as x approaches c, which is this right over here, is not equal to f of c. So once again, this would not pass our test. And here, any of the interior points would pass our test. The limit as x approaches this value is equal, the limit as x approaches that value is indeed equal to the function evaluated at that point. So it seems to be good for all of those. Now let's give a definition for when we're talking about boundary points. So this is continuity for an interior point, and let's think about continuity, I'll do it right over here, continuity at boundary, or let me call it endpoint actually, that would be better. At endpoint C. So let's first consider if it's a left endpoint. If left endpoint, so what am I talking about? A left endpoint. Let me draw my axes, x-axis, y-axis. And let me draw my interval. So let's say this is the left endpoint of my interval. This is the right endpoint of my interval. And let me draw the function over that interval. Looks something like this. So when we talk about a left endpoint, we're talking about our c being right over here. It is the left endpoint. So if we're talking about a left endpoint, we are continuous at, C means, or to say that we're continuous at this left endpoint C, that means that the limit of f of x as x approaches c, well, we can't even approach c from the left-hand side. We have to approach from the right. Is equal to f of c. And so this is really kind of we can only approach something from one direction, so we can't just say the limit in general, but we can say the limit from one side. So it's really very similar to what we just said for an interior point. And we see over here, it is indeed the case, as x approaches c, our function is approaching this point right over here, which is the exact same thing as f of c. So we are continuous at that point. What's an example where an endpoint where we would not be continuous at an endpoint? Well, I can imagine a graph. That looks something like this. So here's our interval. And maybe our function. So at c, it looks like that. There's a little hole right there, and then it looks something like that. Or there's no hole. The function it has a removable discontinuity right over there. At least visually it looks like that. And you see that this would not pass the test because the limit as we approach c from the positive direction is right over here. That's the limit. But f of c is up here. So f of c does not equal the limit as x approaches c from the positive direction. So this would not be not continuous. And you can imagine, what do we do if we're dealing with a right endpoint? So we say we're continuous at right endpoint C if, so let me draw that. Let me do my best attempt to draw it. So This is my x-axis. This is my y-axis. Let me draw my interval so that I care about. Say it looks something like this. A right endpoint means c is right over there. And we can say that we are continuous. We are continuous at x. The function is continuous at x equals c, means that the limit of f of x as x approaches c. Now, we can't approach it from both sides. We can only approach it from the left-hand side. As x approaches c from the negative direction is equal to f of c. If we can say that, if this is true, then this implies that we are continuous at that right endpoint c, and vice versa. And if a situation where we're not, well, you could imagine instead of this being defined right at that point, you could say the function jumps up, just like we did right over there. So once again, continuity, not a really hard to fathom idea. Whenever you see the function just all of a sudden jumping, or there's kind of a gap in it, it's a pretty good sense that the function is not connected there. It's not continuous. But what we did in this video is we used limits to define a more rigorous definition of continuity.